Okay, for this video, I want to go over some of the barriers and challenges that viruses have to overcome. That way they can establish an infection. And then once they do, where do they travel to? How do they get about moving through the body there? And then finally, how do they get out of the host and into a new host? As I mentioned, viruses have these barriers which they have to overcome, and we group them into three broad categories. We have physical, anatomical barriers that they would have to get past, and an example of this might be the skin. We have this layer of dead or dying keratinocytes on the outside there of the epithelium, and this will slough off throughout the day. So as viruses infect those cells, they really don't get into the underlying basal tissues there, or the basal cell layer of that tissue, because they will kind of get brushed off. And so that's one example of a physical barrier. We have chemical barriers. The low acidity of the stomach, along with its role in metabolism, also serves to degrade and destroy pathogens as they make their way through the alimentary tract. And so these chemical barriers can be a potent deterrent to viral infection. Some of the other ones, well, actually, no, we'll leave it there. And then so these secreted antimicrobial barriers we think of as host-derived proteins or mechanisms which actively will degrade viruses. So antimicrobial peptides like the defensins and antimicrobial enzymes, lysozyme being an example in the tears, will degrade any sort of viral or bacterial pathogen, or it will attempt to at least attack it in some way. And so when a virus does get past these barriers, it's typically through a select few sites. And so one of them being the obvious, a break in the skin is a direct route into the underlying tissues, through the respiratory route, like we're seeing now with SARS-CoV-2, through the eyes, even though they're bathed in these antimicrobial enzymes and small molecules which try to deter or stop pathogens from spreading, they can still get and become a site of infection. The gastrointestinal tract, of course, we eat something and wind up getting infected that way. That's a common one for something like polio. We have urinary tract infections, which target that urogenital tract. And then last here I have blood transfusions. Although not a natural route of infection, if you were given a blood transfusion, though, in a hospital setting, you may wind up with an infection from a virus you previously didn't have. While they do screen these blood transfusion, donated blood and plasma, they screen it for some of the pathogens like HIV, for example. They don't screen for everything, though, and I think that just sort of reiterates the point which I made in one of my earlier videos, that all viruses aren't bad. Just because something's a virus doesn't necessarily mean it's bad. Even though it still is a parasite, it might not cause any harm to the host cell. And so a lot of those viruses you might receive in a blood transfusion are, absolutely harmless, or our immune systems deal with them easy enough. Once a virus gets into the host, it needs to infect cells, and we call the range of cells and tissues that a virus can infect the tropism of the virus. And two parameters really determine what the virus can infect. It is these two terms we call susceptibility and permissivity. So for a cell to be susceptible to infection, it must express the receptor which the virus needs to bind to. Using the example of SARS-CoV-2 here, we have the human cell which the virus wants to get into, and its receptor is the ACE2 receptor. It's a natural, host-made receptor, and it's required for normal physiology. Viruses, though, will have evolved to bind to those receptors, because when things bind to these receptors, they get brought into the cell, sometimes, in some cases. And so in this case, the virus has a protein which it's evolved to fit nice and snugly into the ACE2 binding pocket, and it gets internalized that way. And so that means that cell is susceptible to infection. A non-susceptible cell, therefore, is one that does not express the receptor. The other parameter is permissivity, or permissive cell. Just because a virus is in a cell doesn't necessarily mean it's going to have a productive replication and life cycle. And I think both of these points are illustrated really nicely in the lab. We can put genes into a cell for a specific receptor that it might not express normally, and a virus which requires that receptor will now invade that cell, and that's demonstrating susceptibility through the viral receptor. And alternatively, we can take cells which do not express the receptor required, but we can directly inject the virus into the cytoplasm of the cell, and this will be permissive and allow the virus to grow, even though it normally wouldn't be able to get in there. And that's so just giving you an example of why those terms matter. So once a virus is into the host, it needs to spread beyond its primary site of infection. So the primary site is where it first was able to, and we call any infection beyond that primary site a disseminated infection. If that disseminated infection winds up spreading throughout the majority of the body, we would call that a systemic infection. And specifically, you might hear this term, viremia. This is when virus is found in the blood, so you have infectious virus particles in the blood. That brings up the two common modes that viruses do spread throughout the body, which are through the hematogenous route or through the blood. That's another way of saying blood, hematogenous. And then the neural spread, like something like rabies would spread through neurons. So you get a bite wound in your leg from a rabid animal. That primary site of infection winds up disseminating into maybe the local peripheral nerves, and from there that virus infects nervous tissue all the way up into the central nervous system and then the brain. And so it spreads through that neural route, and the other route was hematogenous. Once the virus has spread, it has to, all along this process, it has to continue infecting host cells and getting out of host cells. And there's two main ways that we see viruses doing that. One is illustrated by the background photo here. We see these bacteriophages I've shown before. It's really neat. And they were infecting this bacterium here. And once that viral load has reached a certain threshold in that cell, it will do something that we call lysing, or to lyse the cell. And that the active process of that would be lysis, cellular lysis, and we call these viruses lytic viruses. Again, all just describing their nature to explode out of the cell rather than leave quietly. Contrasting that then would be something like a budding virus, influenza A virus, or the SARS-CoV-2 virus. It buds from the host cell with those host-derived lipids, those lipids which make up the outer envelope. And so this is a less dramatic exit from the cell and egress, which usually leaves the cell alive for at least a little while. So the main areas that we would see these viruses being transmitted would be through basically bodily fluids. We have respiratory secretions which contain viruses. That's probably more common and obvious to some people, but the virus leaves through those mucosal routes, so like through the respiratory tract is one of them. Saliva, something like CMV, can spread through saliva. Feces is a pretty common route. We call these fecal-oral transmission routes. So you ingest the virus through your mouth because it was in some feces that you may have come in contact with without knowing, and then it gets into your intestinal tract and it winds up leaving that way. Less intuitive, maybe. Urine. We can lose viruses through urination, and I think CMV is another one that can spread that way. Blood is an obvious one. Semen and vaginal secretions. These are your sexually transmitted diseases for the most part. Maybe less intuitive again would be breast milk. So babies who are feeding from their mothers can pick up certain viruses that are secreted through that route. One example that I know of was during the last Ebola epidemic, which may be even still ongoing in Africa, there were children who were coming down with Ebola and dying from Ebola who had never come into contact with anybody that was known to be infected, except for the mother, and they were breastfeeding from the mother. And then last would be obviously skin lesions. If you have a big broken sore and you're bleeding through there for a number of reasons, you're going to lose viruses through an open wound. So those are the main topics I wanted to cover for this video, and in the next one I'm going to start discussing how a host cell knows and detects that it's been infected by a virus, and what signals are generated and how it reacts to that. All right, thanks for listening.